In today's lecture, we will see the concept of two important quantum numbers. Actually, the first quantum number is called Lepton number and the another is Baryon number. Lepton number is defined for leptons and Baryon number for baryons. We will also see that these two quantum numbers, Lepton number and Baryon number, remain conserved or remain constant in all the three interactions, that is electromagnetic interaction, the strong interaction and weak interaction. And so you can say that the number of the lepton number and the baryon number will remain conserved in all the known processes. So this conservation principle is also a criteria on the basis of which you can decide that a particular process will take place or not. That is, we can decide that the given process is allowed or forbidden. So this is a very important concept, and the question based on this concept is always asked in the different examinations like civil services examination, or you can say the university examinations and the NET JRF examination. So this is a very simple concept. You can remember something and then you may be able to answer all those questions. So let us start first of all to know about the lepton number and the conservation of lepton number. When we have discussed actually the classification of elementary particle, then you have seen that the fermions are actually of two types, and those are leptons and baryons. Now in the category of leptons, you know there are actually three types of particles. First one is electron and its antiparticle, that is E minus and E plus. Second is actually mu meson, that is mu minus and its antiparticle mu plus. The third one is the tau meson, that is tau minus and its antiparticle tau plus. Okay, and corresponding to each these leptons we define neutrino. So here I have written nu and nu bar. This is neutrino and antineutrino. But remember, when you say electron, then corresponding to this electron neutrino is written as nu e, and its antineutrino will be nu e bar. Similarly, corresponding to mu minus, the neutrino is written as nu mu and the antineutrino as nu mu bar. Similarly, for tau minus, you define the neutrino as nu tau and its antiparticle just as nu tau bar. And all these neutrinos are actually different. So in the category of leptons, there will be actually there will be three pair of neutrino and its antineutrino. Okay. Now how this lepton number is defined, or how this is written. Actually, we denote the lepton number by the symbol L, capital L, and it is defined as number of leptons minus number of anti-leptons. Okay. Now in broad sense you can say that this lepton number L is equal to plus 1 for leptons. Okay. For any lepton it is plus 1, and this will be minus 1 for anti-lepton. Okay. For anti-lepton, any anti-lepton, its value will be minus 1. And this is 0 for all other particles. All other particles, lepton number is 0 for all other particles. Okay. But we define this lepton number particularly for the different leptons. It means when you talk about electron and its antiparticle and its corresponding neutrino, then this lepton number for electron is denoted by the symbol Le, and this Le will be plus 1 for electron and its associated neutrino, that is nu E. Okay, and it is minus 1 for E plus, that is anti-electron, which is called positron, and its anti-neutrino, that is nu E bar. And for all other leptons, if you talk about mu minus, mu plus, tau minus, tau plus, for these leptons, Le will be 0. Remember, when in any process electron will exist, then we have to find the lepton number Le. And if in that reaction there will be in fact mu minus also, the value of Le for mu minus will be 0. Remember it. Okay. So separately, this lepton number is defined for different type of leptons. Now, in similar manner, you can define the lepton number L mu, that is lepton number for the mu meson. And this is plus 1 for mu minus and its associated neutrino, that is nu mu. And it is minus 1 for mu plus and nu mu bar. Okay, and it is 0 for all other leptons. Okay, and similarly, if you are talking about the tau meson, then this is denoted by the symbol L tau, and that will be equal to plus 1 for tau minus and nu tau, that is neutrino associated with tau minus, and it is minus 1 for the anti-tau meson, that is tau plus, and anti-tau neutrino. Okay, and it will be 0 for all other leptons. And if in any process there will be any other particle that is other than any lepton, then we have to take the lepton number for that particle equal to 0. Okay. Now, the conservation principle of this lepton number is valid in all types of all the three interactions, that is electromagnetic interaction, the weak interaction, and the strong interaction. And this conservation principle simply states that in any process, the total lepton number Le, L mu, and L tau remain conserved separately. It means in any process, the total number of Le, that is before the process the total value of Le, and after the process total value of Le will be same, or you can say that change in Le will be equal to 0. Or similarly, change in L mu will be also equal to 0, and similar manner change in L tau will be also equal to 0. So the total lepton number remains conserved in any process. So if you find that in any process delta Le is equal to 0, that process will be allowed. But if delta Le is not 0, that process will be forbidden, that will not proceed. And similar manner, you can check that any process is allowed or not allowed on the basis of L mu and L tau. Okay. Now we will illustrate this fact by taking some important examples. Actually here in all examples we will see that the lepton number remains conserved, so all the processes which we have considered here will be allowed. But there may be some process in which the lepton number will not remain conserved, and that process will be forbidden. But such example we will see later on when there will be a session on question answer. Then we will actually consider those examples. So let us see some of the important examples for the to clarify the concept of uh, conservation of lepton number. The first example I have taken here, neutron decay. You have studied the beta decay process. You know, inside a nucleus, a neutron is transformed into a proton, and at the same time electron and the anti-neutrino corresponding to the electron, which is called actually anti-neutrino electron, that is created and emitted. Now see, this process is allowed on the basis of the lepton number Le or not. Here actually electron is produced, so we have to find Le. We will not think about L mu and L tau. You have only to think Le. Now you know that a neutron is not a lepton. It is actually a baryon. It is a nucleon. So, and you have seen that actually the lepton number for a particle which is not a lepton is simply 0. So as neutron is not a lepton, so Le for this neutron will be 0. Similarly, proton is also a nucleon. It is a baryon. It is not a lepton, and so the lepton number Le for proton will be also 0. But you know that electron is a lepton, and so for this lepton number Le will be +1, and this nu E bar is the anti-neutrino corresponding to the electron, and you have seen just now that for the anti-neutrino corresponding to electron, the lepton number Le is -1. So I have written here the lepton number for the particles existing in this process. Now let us see that before the process, the total lepton number LEI, I means initial, this was simply equal to 0. And when we write the value of total Le after the process, that is LEF, what is this? This will be 0 plus 1 minus 1, and that is also equal to 0. So you can see that actually the total lepton number before this process and after this process is equal to 0. So lepton number remains conserved. In other words, you can say that the change in the value of Le is equal to 0. And since change in Le is 0, so this process will be allowed. On the basis of lepton number, this process is allowed. Okay. Now let us see another important example, which is pion decay. In fact, pion pi minus is decayed into mu minus and nu mu bar. Now you can see pion is not a lepton, okay, and so its lepton number L mu will be equal to 0. Here we will not find Le, because in this process you can see the lepton mu minus is involved, so you have to find L mu, okay, and for this mu minus is since a lepton, so lepton number L mu will be +1, and nu mu bar, this is in fact anti-neutrino corresponding to this mu meson, and so its lepton number is -1. And here you can see that the initial value of the lepton number L mu is 0, and the final value is +1 -1, and that will be simply equal to 0. Okay, so in this process too you can see that the change in lepton number L mu is equal to 0, and so this process is also allowed on the basis of lepton number. So lepton number L mu remains conserved in this process. Okay. Now see the third example, which is muon decay. Here actually this mu minus is transformed into E minus and nu mu and nu E bar. Now you can see mu minus is a lepton and E minus is also a lepton. So in fact, in this process, two types of leptons are involved. So we will see that this process is allowed or not on the basis of two lepton numbers, one for the uh, electron and another for the mu meson. Okay, so you have to find the value of both Le and L mu in this process. Okay, are you getting the things? Okay, see, when you talk about Le, as I have told you just now, that if you write the value of Le, then for any other leptons, the value of Le will be 0. Okay, so you can say that since mu minus is also a lepton, but this is not a electron, so if you write the value of Le for mu minus, that will be equal to 0. Okay, and for electron it will be plus 1, and since this neutrino is corresponding to mu meson, so the value of Le will be 0. But nu e bar, this is the anti-neutrino corresponding to electron, so the value of Le for this will be minus 1. So what you are seeing here, the sum of the values of Le before the process was 0, and after the process you can see this is 1 plus 0 and minus 1, and you can see this will be simply 0. So in this example you can see that this change in Le is equal to 0. So this process is allowed on the basis of the lepton number Le. Okay, again, since mu minus lepton is also involved in this process, so we have to also find the value of L mu to check that this process is allowed on the basis of value of L mu or not. Since mu minus is a lepton and we are finding the value of quantum number L mu, so for mu minus you know this is equal to plus 1. But electron is although a lepton, but we are talking about L mu, and you have seen if you write the value of L mu for any other lepton other than the mu meson, then that will be 0. You have just seen it. I am just turning the page and you can see I have mentioned here that actually L mu is equal to 0 for all other leptons. Okay, so from this fact you can write that this L mu for E minus will be 0, and nu mu, this is the neutrino corresponding to mu, so in fact it will be equal to plus 1, and nu E bar, this is the anti-neutrino corresponding to electron, so for this L mu will be equal to 0. So see, before the process the total lepton number L mu in this example is 1, and after the process what is the value? You can see this is 0 plus 1 plus 0, it means simply 1. So here also you can see that the change in L mu is also equal to 0. 1 minus 1, that will be 0. So this process muon decay is allowed on the basis of the lepton number Le and L mu, since both of Le and L mu are conserved in this process. Okay. Now the next important example is pair production. You know, in case of pair production, a gamma photon is transformed into electron and positron. Now since here electron and positron, that is antiparticle of electron, is involved in this reaction, so you have to calculate only the value of Le. Since gamma is not a lepton, you know, this is just photon, that is a boson, so for this Le will be 0, and for electron you know Le is equal to +1, and for anti-electron it is -1. So before the process the total value of Le was 0, and after the process you can see this is +1 -1, and that will be simply equal to 0. It means the value of Le before the process and after the process remains same. So you can say that change in Le in this process will be 0. So Le remains conserved, and so this process is also allowed on the basis of lepton number. Okay. Next important example I have taken here, kaon decay. In fact, in this process K0, this kaon is transformed into pi plus E minus and nu E bar. Now K0, you know this is not a lepton, and so Le will be equal to 0, and pi plus is also not this pi plus is also not a lepton, and so this value of Le for this will be also 0. And electron is a lepton, and we are finding the value of Le. So for this electron it will be +1. For anti-neutrino corresponding to electron it will be -1. So what is the initial value of Le? This is 0. And what is the final value? You can see this will be 0 plus 1 minus 1, and this will be simply 0. So in this example 2, change in Le is equal to 0, and this process will be also allowed. Okay. Now you can see the decay process of proton. In fact, you have studied this process in case of beta decay, that when positive beta is emitted, then a proton is converted into a neutron, and this positive beta particle, that is positron, is created, and at the same time neutrino corresponding to the electron is created and emitted. Now proton, you know this is a nucleon, that is a baryon, not a lepton. So for this Le is equal to 0, and neutron is also a nucleon and or baryon. So for this Le is 0, and as E plus is the antiparticle of electron, so this is anti-lepton, and for anti-lepton this Le will be -1, and nu E is in fact neutrino, not anti-neutrino. So for this Le will be +1. So here you can again see the initial value of Le is 0, and final value is 0 minus 1 plus 1, which will be simply 0. You can check, and therefore change in change in Le, that is delta Le, is 0, and so this process is also allowed. Okay. Now we consider pion decay. In fact, pi plus is converted into mu plus plus nu mu. Since here pion, that is pi meson, is actually involved, so we will talk about the lepton number L mu, not Le. Okay. Now see, pion, pi plus is not a lepton, and therefore for this L mu will be 0, and mu plus, this is anti-lepton. Okay. So for this L mu will be -1, and nu mu, this is actually the anti-neutrino corresponding to muon, and therefore for this L mu is +1. So you can see that before the process the total lepton number L mu is 0, and after the process it is also 0, because -1 plus 1, that will be equal to 0. So in this example 2, you find that the change in lepton number is equal to 0. So this process is also allowed on the basis of conservation of lepton. Now we will see the conservation of baryon number. You know that just like lepton number, we define a very important quantum number which is called baryon number for baryons. And we have seen that the family of baryon includes which particles, when we have discussed actually the classification of elementary particles. You can see that actually baryons are broadly classified into two categories. First one is nucleons and another is hyperons. You can see. And you know that nucleons are of two types. First one is proton and another is neutron. And here actually this P minus is anti-proton and this new N0 bar is anti-neutron. Okay. Now hyperon is actually broadly of three types. First one is called lambda hyperon and this is denoted by the symbol lambda 0. Another is sigma hyperon and the third one is called actually xi hyperon and the fourth one is omega hyperon. You know. Further, this sigma hyperon is of three types. These are sigma plus, sigma minus, sigma 0. And this xi hyperon is actually of two types. This is xi minus and xi 0. All these things you have studied during the study of classification of elementary particles. Now, as I have mentioned here, the anti-proton and anti-neutron corresponding to proton and neutron, just like that, for all these hyperons, there will be also the antiparticle. Okay, I have not mentioned in this figure the antiparticle, but corresponding to each and every hyperons, there will be anti-hyperons. Okay. Now, how this baryon number is defined? Actually, this is just defined like the lepton number. Baryon number is denoted by the symbol B and it is defined as number of baryons minus number of antibaryons. Okay. Now see, actually this baryon number B is equal to +1 for all normal baryons. Okay, all baryons, its value will be +1. That is, you know, baryons are P plus N0, lambda 0, sigma plus, sigma minus, sigma 0 and xi minus, xi 0 and omega minus. These are actually the baryons. And for all these baryons, this baryon number is equal to +1. And corresponding to every baryon, we define antibaryon. And so, for antibaryons, this baryon number is equal to -1. It means when you will find the, we will write the baryon number for, let us say, P minus, that will be -1. When you will write the baryon number for N0 bar, that will be equal to -1. Okay. Similarly, if you write the baryon number for lambda 0 bar, that will be -1. Okay. So corresponding to all these baryons, we have antibaryons, and for all those antibaryons, the baryon number is simply equal to -1. And if any process, the particle involved is not actually a baryon, then we will write the baryon number be equal to 0 for all those particles. It means if the particle is not a baryon or antibaryon, then the baryon number will be simply equal to 0. This is very easy to remember. Okay. You have definitely understand that for all baryons it is +1. For all antibaryons, baryon number is -1. And for all other particles, it is simply 0. Okay. Now, the conservation principle of baryon number is also of universal nature. It holds in case of all the three interactions, that is electromagnetic, weak and strong. We are not talking about the gravitational interaction, because I have told you that in case of the study of interaction of elementary particle, the gravitational interaction plays no role. So I talk about only three interactions which has significance in case of the interaction of elementary particles. So this conservation principle holds in all the three types of interactions, and so this is also of universal nature. Okay, and what is this conservation principle? Actually, the conservation principle of baryon number simply states that in all processes the baryon number remain constant. Okay, it means when the process will proceed, the change in baryon number must be equal to 0. So you can say that the total baryon number before the process and total baryon number after the process will remain same. This is the simple statement of the conservation principle of baryon number. Now we will illustrate this statement by some important examples, and as I have told you that in your examination there will be the reaction will be given and you have to ask that check the baryon number in this process is conserved or not, and or in other words you will be asked that this process is possible, this process is allowed or not allowed on the basis of baryon number. You have to check. So let us see. The first example I have taken here simply the neutron decay, that is beta decay process. Here neutron is converted into proton, electron and anti-neutrino. Okay. Now write the baryon number of all these particles. See here, I am writing the number of the value of B for all these particles. Since N0, that is neutron, is actually a baryon, and you have just seen that for any baryon number B is plus 1. So for this N0, baryon number will be plus 1. Again, P plus, this is also a baryon. So for this baryon number will be plus 1. But electron and anti-neutrino corresponding to the electron, these are not actually baryons, these are other particles. Okay, and you have seen that for other particles baryon number is equal to 0. So for electron B will be 0, and for anti-neutrino corresponding to electron will be also 0. So you can see that before this process the total baryon number was plus 1, and after the process this is 1 plus 0 plus 0, and this is simply equal to 1. So you can see that this baryon number remains conserved, and so we can say that delta B in this process is 0. Delta B means change in baryon number. Final baryon number is 1 and initial baryon number is also 1. So this change will be equal to 0. And so this process is allowed on the basis of baryon number 2. And you have seen earlier that this process is also allowed on the basis of lepton number. So you can see that this beta decay process is allowed both on the basis of lepton conservation and lepton number conservation and the baryon number conservation. Both conservation principle allow actually the beta decay process. Okay. Now see some extra examples here. Here you can see this reaction. Pi 0 plus N0 equal to K0 bar plus sigma 0. You know that pi 0, this is not a baryon, so for this baryon number will be 0. N0 is a baryon, so for this B will be equal to 1. K0 bar, it is not a anti-baryon or baryon, so for this B will be 0. But sigma 0 is a baryon, and therefore for this B is plus 1. So you can see before the process the baryon number was 0 plus 1, that is 1, and after the process this is 0 plus 1, that is 1. So change in baryon number will be 1 minus 1, that is 0, and so this process will be allowed. Now see this process. Lambda 0 is decayed into proton and pi minus meson. You know that lambda 0, this is in fact a baryon, and so for this B is equal to plus 1, and proton is also a baryon, and for this again B will be plus 1, but pi minus is not a baryon, so for this B is equal to 0. So you can see before the process the total baryon number is 1, and after the process it is again 1, because 1 plus 0 will be 1. So change in baryon number will be 1 minus 1, that is 0. So this process is also allowed. Baryon number remains conserved in this process. Okay. Now see this process. If you consider that this lambda 0 is transformed into P minus and pi plus, then what will be the baryon number of the different particles? You can see lambda 0, since you know that this lambda 0 is a baryon, so the baryon number is plus 1, and P minus, this is anti-proton, it means anti-baryon, and for any anti-baryon, baryon number B is equal to minus 1. Here actually I have written the value of baryon number, and pi plus is not a baryon, and for if it is not a baryon, so B will be simply 0. So what you are seeing here, before the process the total baryon number is plus 1, and after the process this will be minus 1 up plus 0, that is minus 1. So final baryon number is minus 1 and initial baryon number is plus 1. So what will be the change in baryon number? This will be minus 1, that is minus 2. It means delta B in this process is not equal to 0. So baryon number in this process does not remain conserved. And as baryon number does not remain conserved, but you know according to the conservation principle of baryon number, in all processes the baryon number should remain conserved. So this process is forbidden, it is not allowed. This process will not proceed. On the basis of conservation of baryon number, you can decide it. Okay. Now again see this process where a proton is transformed into an anti-electron, that is positron, and a gamma photon. Since P plus is a baryon, so for this baryon number is 1, and since E plus is a lepton, it is not a baryon, so for this this baryon number is 0, gamma photon is also not a baryon, so for this B will be also 0. So initial value of baryon number in this process is 1, and final value will be 0 plus 0, that is 0. So what will be the change in baryon number? This will be 0 minus 1. Final value is 0, initial is 1. So change will be 0 minus 1, that is minus 1. And so you can say that in this example, delta B is not equal to 0, which implies that the total baryon number does not remain conserved in this process. And since the baryon number does not remain conserved, so according to the conservation principle of baryon number, this process will be not allowed. It is actually it is forbidden. Okay. So I hope you have understand this very simple concept of the conservation of lepton number and baryon number. The concept is very simple, but it is very useful for your examination purpose. And in the forthcoming lecture, we will see some other conservation principle which will be also very important for you.